Hey everyone, and welcome. Today we're going to fire up the boilers and get right into the heart of how our world gets its power. We're talking thermal power plants. Let's dive in. Have you ever really stopped to think about it? It kind of seems like magic, right? You burn something like natural gas and poof, the lights switch on in your house. So what's the trick? How do we get from a simple flame to the massive electrical grid that powers everything? Well, the secret isn't magic. It's actually a set of brilliant, surprisingly elegant, you could almost call them engineering recipes. And these recipes, called thermodynamic cycles, are basically the blueprints for turning heat into motion and then into electricity. So what exactly is a thermodynamic cycle? Okay, imagine you have some stuff, let's say water. You take that water on a round trip. You heat it up, let it expand, then you cool it down, squeeze it back together, and it ends up exactly where it started, ready for the next lap. And here's the key. Along that journey, it takes some of that heat energy and turns it into useful work, like spinning a giant turbine.
Now, to understand the recipes we actually use, we first have to look at the ultimate 5-star Michelin recipe, the one that's theoretically perfect, but, well, you can't actually make it. This is the Carnot cycle.
The Carnot cycle is basically the universe's speed limit for engines. The laws of physics tell us you can never turn 100% of heat into work. It's just not possible. The Carnot cycle tells you what the absolute best-case scenario is. It's the gold standard, the perfect score that every real engine is graded against. And how does it achieve this theoretical perfection? Through 4 very specific, completely perfect steps. You add heat while keeping the temperature rock steady. That's isothermal. Then you let it expand without any heat getting in or out. That's adiabatic. Then you do the same thing in reverse. Remove heat at a constant low temp and then compress it with no heat transfer to get right back to the beginning. It's a beautiful, perfect little loop.
But, and this is the big but, it's all just a theory. In the real world, you can't have these perfect, slow, totally frictionless processes. It's just not possible. The source material puts it bluntly. No real engine can actually be built this way. So if Carnot is the impossible dream, what do engineers actually build?
And that question brings us crashing right back into the real world and to the Rankine cycle. This isn't some theoretical fantasy. This is the cycle that powers the vast majority of steam power plants all over the globe. This is the workhorse. Seriously, anytime you see one of those massive power plants with the huge cooling towers, chances are you are looking at a Rankine cycle in action. It is the absolute go-to recipe for making electricity from steam. So instead of Carnot's perfect imaginary steps, Rankine uses real physical hardware. First, a pump puts liquid water under a ton of pressure. Second, a boiler heats that water up, turning it into super high-pressure steam. Third, and this is the good part, that steam blasts through a turbine, spinning it like crazy to generate power. And finally, a condenser cools all that steam back down into water so the pump can grab it and start the whole trip all over again.
But here's the thing. Even this super practical cycle has an on-paper version and a real-world version. The ideal Rankine cycle assumes every part is 100% efficient. But in reality, pumps and turbines have friction, pipes lose pressure, heat leaks out, and all those little imperfections add up and reduce how much power you get out at the end. It's a constant battle for engineers. So how do you fight that battle? How do you squeeze out more efficiency? Well, you get clever. And one of the most common tricks is to add a little twist to the recipe. It's called the reheat Rankine cycle. The core idea here is so simple, it's kind of genius. After that steam has already gone through the turbine and done some work, it's still pretty hot, right? So what if you just send it back to the boiler to heat it up again? You give it a second wind, more energy to do even more work. Here's how it works in practice. Instead of one big turbine, you basically use 2. The super hot, high-pressure steam goes through the first, high-pressure turbine. But before it goes to the condenser, you pipe it back to the boiler for a reheat. Then, this refreshed, superheated steam drives a second, low-pressure turbine. It's a way to squeeze every last drop of energy out of that steam. Okay, let's completely switch gears. So far, our main ingredient has been water, right? We boil it into steam, but what if we used a different ingredient? What if we used air? This brings us to a whole different recipe book and the Brighton cycle. The Brighton cycle is the secret sauce behind every jet engine, and for us, behind every gas turbine power plant. There's no boiler, there's no condenser. This cycle works directly with air and hot gas. It's this incredibly fast and powerful 3-step process. First, a giant compressor sucks in and squeezes a massive amount of air. Second,
Fuel is sprayed into that compressed air and ignited. Whoosh, you get a super hot, high-pressure gas. And third, that hot gas blasts through a turbine, expanding and spinning it at insane speeds to make electricity.
Okay, so we've got our steam recipe, the Rankine cycle, and we have our gas recipe, the Brayton cycle. What do you think happens when a brilliant engineer decides to combine them? You get the single most efficient thermal power plant we have in common use today, the combined cycle.
Think about it for a second. That exhaust gas coming out of a gas turbine, it is screaming hot, hundreds and hundreds of degrees. Just letting all that heat go out into the atmosphere is like throwing away free energy. So the genius question behind the combined cycle is, what if we could capture that waste heat and use it to power a whole second engine for free?
And here's the beautiful part. You have a gas turbine running on the Brayton cycle, making power. But its super hot exhaust doesn't get wasted. It's channeled into a special boiler, a heat recovery steam generator. And that exhaust heat boils water to make steam, which then powers a second steam turbine, running on the Rankine cycle. It's incredible. You're getting power from two different cycles, but you're only paying for the fuel for one.
And the result? It's just a massive, massive jump in efficiency. A standalone steam plant or gas plant might be happy to hit 40% efficiency. But these combined cycle plants, they routinely get over 50%, and the newest ones are even pushing past 60%. That's a huge deal. It means less fuel burned and fewer emissions for every kilowatt hour of electricity we use.
So there you have it. We've gone from the perfect, impossible dream of the Carnot cycle to the real-world steam workhorse of the Rankine cycle, and finally to the ultra-efficient hybrid of the combined cycle. These engineering recipes have literally built our modern world. But the story's not over. As we push for even better technology, the big question is, what's next? Which of these cycles will power our future, and which ones will just be a chapter in a textbook?